Hello students, now in this video let us see one example and later on we will go for next important definitions. So example is that if GCD of A and B is same as GCD of B and C, that is equal to D suppose, then the GCD of A, B and C should be what? D. This is our example. This one we have to show. So, let us see the proof or the solution for this. Suppose let us assume the GCD of A, B and C is some new element G suppose. Now then if this is the case, then our claim that we have to prove that what we have to prove D equal to what? G. This D equal to G. Fine. That thing our claim. D equal to G. Now as the GCD of A and B is equal to D, so this gives D divides A and D divides what? B. If D divides A and B means A is equal to what? dk1 and B is equal to what? dk2. Call it as equation number 1. For some, obviously for some k1, k2 belongs to what? Z. These are what? Integers. Now also the GCD of B and C is what? D. So that also gives D divides B, D divides what? C. So that gives B is equal to dk3 and C is equal to what? dk4. Let it be equation number 2. For some k3, k4 belongs to what? Set of integer. Fine. Now what we have assumed, the GCD of A, B, C is what? G. Therefore, by existence theorem, what we get? By existence theorem, we get AX plus BY plus CZ is equal to what? G. AX plus BY plus CZ is equal to G. Fine. That is the linear combination theorem. Now let us substitute the value of A, B and C from this equation 1 and 2. So that gives dk1x plus dk2y plus dk4z, that is equal to what? G. Using 1 and 2. Using 1 and 2. This is the reason for this step. Now from this we can take D common. D will be common. K1x plus K2y plus K4z, that is equal to what? G. That is same as D divides what? G. Call it as equation number 3. Now we get D divides G. Again, now the next part. Again, as the GCD of A, B and C is what? G. So this gives this G divides A, G divides B and this G divides what? C also. Fine. Now as G divides A, so we get A is equal to G times some integer, B is equal to G times some integer and C is equal to G times some integer. Fine. For some k5, k6 and k7, what? These are integers. Fine. And call it as equation number 4 suppose. Fine. Now and this GCD of A and B is what? D. This is given to us. GCD of A and B is what? D. Therefore, by existence theorem, existence theorem, what we get? Ax plus by is equal to what? D for some x and y in z. Fine. Now let us substitute the value of a and b in terms of g here. So it will be gk5x plus gk6y, that is equal to what? D. So let us take g common. G will be common. k5x plus k6y is equal to what? D. So that gives G divides what? D. Call it as equation number 5. Now equation 3 and 5 gives us D is equal to what? G. Therefore from equation 3 and 5 we get what? D is equal to G. This is our requirement. That is, the GCD of A, B and C should be what? D. GCD of A, B and C must be D. This is the answer of this example. Now let's go for the next and the important. The definition is of the residues of A modulo M. Now definition. The definition says if A congruence to B modulo M, then this B is called residue of A modulo M. In simple language we can say this B is nothing but what? The remainder here. What we get here? M divides A minus B. So A minus B is equal to M into K. Look at here. M divides A minus B. That is A minus B is equal to M into K. Fine. Therefore this A is equal to what? M into K plus B. So if we compare this thing with division algorithm, then we get this B is what? The residue or the remainder you can say. So this B is called the residue of A. The residue of whom? A modulo M. When we divide by M, then we get the remainder will be B to A. A will be dividend. This M is what? The divisor, and B will be what? The remainder. And obviously K is the quotient here. Fine. Now this is the definition. Now from this definition we have some other systems are there. So the first system is what? The complete residue system. And another one is what? The reduced residue system. Let us see the definition of this. What are these are? Now a set of integers x1, x2, so on up to what? Xn is said to be complete residue system. Is said to be complete residue system. This is complete residue system modulo M. If the first condition is that it consists exactly M elements. Clearly here M integers are given to us, but still I will write this because this is important. Then second condition is that xi doesn't congruent to xj. Doesn't congruent to xj modulo M when for all I not equal to what? J. When they are unequal, these are not congruent to each other, means these are not the residues of each other when they are not same. Fine. I is not equal to J. Now the next one is that for every integer y, there exists, for every integer y there exists one and only one xi such that y congruence to xi modulo m. Means what? Now these are some integers, m integers are given to us. Now this y we will take some another integer except these one or excluding these one, y will be some another integer, and when we take when we divide that one with respect to m, or the divisor will be m, dividend will be y, that time we get some residue here, and that residue is nothing but one of these m numbers. That is this third condition. Now let me take an example here. Suppose let m equal to what? 5. M is 5. Then look at, suppose the first thing, now m I will take fixed. Suppose I have the integers 0, 1, 2, 3 and 4. Now these are my integers, suppose just like this, x1, x2, so on up to xm. So these are how many numbers? 5 in numbers. So it consists exactly m elements. M is 5, these are 5 elements. So the first condition is satisfied. We have to check whether it forms a complete residue system or not. That thing. Modulo what? 5. Obviously modulo 5. Fine. Now we have to xi doesn't congruent to xj modulo m. Let us check. Is 0 congruent to 1 modulo 5? What does this mean? This means if this is, then 5 should divide 0 minus 1. That is 5 divides minus 1. But this is not true. So 0 doesn't congruent to 1 modulo 5. Again 0 doesn't congruent to 2 modulo 5. Fine. Also 0 doesn't congruent to 3 modulo 5. 0 doesn't congruent to 4 modulo 5. Or every time this is what? False. Similarly, 1 doesn't congruent to 2 modulo 5, 1 doesn't congruent to 3 modulo 5, 1 doesn't congruent to 4 modulo. It is not possible that the remainder are these numbers. Fine. Now, when we divide by 5, then the remainders are either 0, 1, 2, 3 and 4. So, these numbers doesn't congruent to each other modulo 5. So, the second condition is satisfied. Now, I will take some another integer. Suppose 6. 6 will be taken. Congruence to what? Modulo 5. So 6 congruent to what? 1 modulo 5. The remainder will be what? 1 that time. So 6 congruent to 1. 1 is in between this? Yes, 1 is there. Fine. Now if I take 13, then what about 13? 13 congruent to what modulo 5? Now 13 congruent to what? 3 modulo 5. Why? Because 5 divided by 13 is divided by 5, then the remainder will be what? 3. So we get 3. 3 is here? Yes, 3 is there. So we get, wherever we get here the residue is one of these number. That means this third condition is also satisfied. So what can I say? This 0, 1, 2, 3 and 4 is a complete residue system, modulo 5. This conclusion we can find out. Similarly, now let me take another integers 1, 2, 3, 4 and 5 suppose. Is this one also forms a complete residue system modulo 5? Now it has 5 elements. Now if we take the elements in between these are not congruent to each other. You can check that thing. Now for every integer y, there exists one and only one xi. So obviously modulo 5 will be what? It gives 0. 0 is same as 5 here. You know the what these Z3, Z4, these are what? These are some sets. Which sets? These are the sets with what? the integers, the remainder, what are these? This is 0 bar, 1 bar, 2 bar and 3 bar. These are the elements of this. These are the sets having the remainders left modulo 4. Fine. Same thing is here also. If modulo 4, modulo 5, modulo 3, modulo whatever it, then the remainder will be what? The least number. And that time 5 is nothing but equivalent to 0. So is a complete residue system, is a complete residue system modulo 5. Modulo what? 5. Now let us check for 3. Suppose let us check through 3, 4, 5 and 6 is, what about this? Now if we check this, these are also 5 elements. Now 2 doesn't congruent to 3, 2 doesn't congruent to 4 modulo 5, 2 doesn't congruent to 5 modulo 5, 2 doesn't congruent to 6 modulo 5. Similarly you can check for others. And also if there is some another integer y and we have to take modulo 5, then we get one of the elements among these one. So this is also a complete residue system modulo 5. Modulo 5. Now this 6 is nothing but 1 here, this 5 is nothing but 0 here. So these are equivalent. These things are isomorphic to each other. Similarly, now I can take these elements also. -1, 0, 1, 2, 3. Means no need to go towards right only. We can go towards left also. We can start from left. -1, 0, 1, 2, 3. This is also a complete residue system. This is also complete residue system modulo 5. Modulo 5. Now if I take the elements 1, 2, 3 and 4. Now here only 4 elements are there. The first condition is not satisfied. So is not a complete residue system, is not a complete residue system modulo 5. Modulo what? 5. Fine. Now let us take the next one. Suppose 0, 1, 2, 4 and 8 is there. Now this 8 is equivalent to whom? 8 congruents to what modulo 5? It will be 3. So this forms, it is isometric to or isomorphic to this one. Therefore is a complete residue system modulo 5. Modulo 5. Fine. Now let me take one more example for this. Now same thing, m will be 5. Let me take one more. These are sixth one is this. Now let me take one more, 7th one. Suppose the elements or the integers are 1, 2, 4, 7 and 9 suppose. Now here these are again 5 elements, m is 5 elements are these. What about xi doesn't congruent to xj when I is not equal to j? Now if I take 7 congruent to what modulo 5? Modulo 5. 7 congruent to whom? 2 modulo 5. So 7 is here, 2 is also here. Now these are not same, but still they are what? Congruent to each other. So this condition will fails. These are not same, but they are here. They doesn't. Here we want they must be incongruent, but here they becomes congruent. So this is not a complete residue system modulo 5. So what can I say? Is not. Similarly for 9 we get the remainder will be 4. Fine. Is not a complete residue system modulo 5. modulo 5. Remember these things. If any one of these conditions is not satisfied, then it is not a complete residue system modulo m, whatever the integers are given to you and the value of m is given to you. Now let us see the remarks from this definition. The remarks are, let us write down one remark. For a fixed positive integer, integer m, there exist an infinitely many complete residue systems, modulo m. There are infinitely many complete residue systems modulo m. Now as m is any number, then I can say 0, 1, 2, 3 up to what? M minus 1. This is also a complete residue system modulo m, just we have seen. Now I can take 1, 2, 3, 4 and so on till m. This is also a complete residue system modulo m. Fine. Also I can take 2, 3, 4, 5 and so on up to what? M plus 1. This is also a complete residue system modulo 5. I can say minus 1, 0, 1, 2, so on up to what? M minus 2. This is also a complete residue system modulo 5 and so on. So either we can go towards right, from right we can take m integers, from left we can take m integers, whatever it, but we have infinitely many complete residue systems modulo m for any fixed positive integer m. Fine. Now this is about the complete residue system. Now the next important definition is of the reduced residue system. What is the reduced residue system? Let us see the definition of reduced residue system. Reduced residue system. Now the reduced residue system, there are also some integers are given to us. A set of non-zero integers. A set of non-zero integers x1, or let me take x1, so reduced is this, so let me take r1, r2, so on up to rk. K integers let us take, is said to be reduced residue system modulo m if the first one is what? Ri m, means what? The GCD of each Ri and m will be what? 1 for all I from 1 to k. If we take the GCD of each that integer with m, then GCD should be what? 1. This is the condition. Then the second condition is that this Ri doesn't congruent to Rj. This is just like a complete residue system modulo m. These elements are not the residues of each other modulo m for all I not equal to what? J. Obviously if they are different, then the congruent should be different. Now the third condition is that if A and m having the GCD 1, then there exists unique Ri such that there exists unique Ri among these, such that if A is any other integer whose GCD with m is what? 1, or they are relatively prime. then there exists unique Ri such that A congruence to whom? Ri modulo M. Now this Ri is from where? Among these R1, R2, so on up to Rk. These are the conditions. Fine. So here let me write one remark from this. Remark: if x1, x2, so on up to xm be a complete residue system, modulo M, then the set of those xi which are relatively prime modulo M, then the set of those xi which are relatively prime to M defines a reduced residue system modulo M. As now in complete residue system, if whatever the value of M, the number of integers should be M, that is the condition. But in reduced residue system, that condition is not compulsory here. This K may be differ than M. These are different things. Here these numbers may be less than what? M. So here what this remark says, if these are M numbers or M integers forms a complete residue system modulo M, then we have to collect such a xi's which are relatively prime to M, so that form or that satisfies this condition. Obviously this second condition will be satisfied by these, as this is a complete residue system. Fine. So simply we have to collect such a xi's here which are relatively prime to whom? M. That is the condition. So that defines a reduced residue system modulo M. This is also hold there. Obviously if that are these are obviously less than whom? M. Fine. Or maybe greater than M, but that will be, though these are such integers which are relatively prime to M, then M is relatively prime with another integer, that time also this gives the same residue among these xi's, any one of these xi's. These are equivalent. Now let us see the example on this. Now let me take example here. For M equal to 5, we know a complete residue system, modulo 5. A complete residue system modulo 5 is, what does that? This is 0, 1, 2, 3 and 4 is this one. This is one set of integer which is a complete residue system modulo 5. Therefore, now you know 1, 0 and 5 are not, but 1 and 5 are relatively prime, 2 and 5 are relatively prime, 3 and 5 are relatively prime, 4 and 5 are also relatively prime. Why I am taking these? Because we know when we take the prime number which is greater than 1 or the relatively prime that are greater than 1, strictly positive are they. So we cannot take 0. So from this we can say a reduced residue system. A reduced residue system modulo 5 is, reduced residue system modulo 5 is what? Is these elements 1, 2, 3 and 4 only. This is the condition here, or this is the remark here. Now let us see some more examples here. Some other examples here. So The other example is that for m equal to 6, we have what? This 0, 1, 2, 3, 4 and 5. This forms is a complete residue system. Complete residue system modulo 6. And which of these will be relatively prime with 6? Now we don't want to take 0, simply we have to think about this one. Now 1 is relatively prime to 6, 2 is not relatively prime to 6, 3 is not relatively prime to 6, 4 is not relatively prime to 6, but 5 is relatively prime to 6. So this 1 and 5 is what? Is a reduced residue system. Is a reduced residue system modulo 6. Now one more thing, let me take for m equal to 8. Now we have to find out such numbers which are relatively prime to 8, less than 8 and relatively prime to 8. So that forms, now 1 will be there, that type, 3, 5 and 7. These are the integers which are less than 8 and relatively prime to 8. So it forms a reduced residue system. Is a reduced residue system modulo 8. That thing I can write, modulo 8. Now this is about the complete residue system and the reduced residue system. This is important one. Now here we will stop. Now in next video we will see the Euler's phi function and some remarks on it, some examples on it and some theorems if we have a time that time. Okay, fine. Thank you.